Yet again, I was wrong, ladies and gentlemen. I was wrong about something in my quantum gravity calculations. I've gotten very, very far indeed with this project, I think. I think I've gotten down to something that's really very satisfactory indeed, which is this parsimony now between Coulomb's law and Newton's law for two hydrogen atoms contained within a 1 centimeter cubed container at a Lagrange point. So at a Lagrange point, the box, the container that the two atoms are contained in will feel no external force of gravity in an idealized setting at least. They'll feel, that's when the gravity from the Earth and the Sun are in balance. So there should be zero gravitational forces acting within the experimentation chamber at all. So we'd, in theory at least, be able to measure the gravity that exists between two hydrogen atoms. So this is the result for the bare force of gravity that I got out of the equations using Newton's law of the inverse square law for universal gravitation. I got 1.6 times 10 to the minus 62 Newton meters cubed per kilogram squared, right? So that's an incredibly small amount of gravity. That's an incredibly weak force. But then I also adjusted for the fact that it would be a secondary electron density surrounding each nucleus, surrounding each atom. That is the part that we can't see, is in essence the atom's gravitational field, where electrons from the atom are tunneling. And I tried to use Coulomb's law then to try and get a figure adjusting for this, dividing over the ratio between the force of gravitational attraction and electrical repulsion, 4.17 times 10 to the 42, and then feeding that result multiplied by the elementary charge into Coulomb's law. And the result I get is 2.216 times 10 to the minus 68 Newton meters cubed per Coulomb squared. So that's very encouraging, isn't it? That seems to me as though those results line up very precisely, quite precisely, by a few orders of magnitude difference, but albeit like very, very close together. There's only a gap there of a very small amount really, and maybe I've been sort of troubling with myself too much over this little gap. It could be caused by not using precise enough values for the elementary charge or something like that. It could be caused by anything really. Could be skewing the equations by a few orders of magnitude. And when it comes to numbers like 10 to the minus 62 and 10 to the minus 68, that's 0.1, then 62 zeros, or 0.62 zeros, then 1, or 61 zeros, then 1. And so that's really, really very fine, precise measurements, very fine, precise results. And maybe I needn't be quibbling about this idea of radiation pressure in the intervening to account for the differences between Coulomb's law and Newton's law at all. Maybe I should just really be satisfied with that sort of result and consider that a unification of gravitation with the force of electromagnetism. And maybe just sort of leave it there and have done with it. However, the little gap there is quite interesting nonetheless. And every time I've run these calculations, it does seem to pop up again and again and again. And I'm just wondering if that is down to radiation pressure, but not the sort of radiation pressure that would be assumed in both Newton's law of gravity and in Coulomb's law. I'm wondering if this might be a different sort of radiation pressure that you shouldn't really call P gamma, but which you should more like call capital lambda. It's the cosmological constant. It's electrons from the background tunneling inside the box, and you can have a light year of lead surrounding this box if you want. You'll never be able to control the cosmological constant. You'll never be able to control this fact that electrons from the background will be tunneling into the box and depositing photons there. So it could just be that little tiny positive cosmological constant that's slightly skewing the results one way or another. Maybe it is that. And somehow Newton's law for universal gravitation accounts for the cosmological constant, albeit to some extent, since we know the values of Newton's gravitational constant to very precise, a very high degree of accuracy, precision. And we know Coulomb's constant to a very high degree of accuracy and precision. However, Coulomb's law deals with charges and the forces between charged objects, what I did with Coulomb's law, I took as my basic proposition that all atoms are fundamentally slightly negatively charged, or have and when it comes down to positive and negative charges, we don't really need to be using positive and negative numbers at all. We can have some idea of absolute charge, since we might as well call positive charge like blue and positive and negative charge like blue and red charge, for instance. They're opposed charges, but they needn't necessarily cancel out in a mathematical way, since that might be somewhat unphysical as an assumption to do that. But nonetheless, I'm very, very encouraged by that result that you can see at the top there. This business with Coulomb's law and Newton's law. I don't know if you can see that properly, but it's almost there. It's still within a very, very high degree of precision. 10 to the minus 68, and having it's just like an error bar, isn't it? It's like it doesn't matter almost. I don't think. I think it's so close. It's so close using the assumptions that I've invoked, using I think what was really my masterstroke in physics, which goes back many years, is developing this equation, this time dependence and time independent equation for the secondary electron density, which is what I call it. The number of atoms multiplied by the average atomic number over 4.17 times 10 to the minus 42. Take that, multiply it by the electric charge, the charge of the electron, i.e., then you gain an estimate for the field strength of gravity within the box. Then you feed that into Coulomb's law with the elementary charge again on top of the equation, divide that by the range between the two atoms, which we're assuming is 0.01 meters, i.e. 1 centimeter. Then you get 2.216 times 10 to the minus 68 Newton meters cubes per Coulomb squared. So, that's it. That's the force of gravity. I mean, with a couple of new assumptions added in, it does work out. It does hold up to analysis, to scrutiny, I think. Well, I think I've proven that, pretty much. I mean, that's the point of publishing research. That's what I'm going to try and do, try and get all this published somehow. And, it comes down to something really quite simple. It comes down to this idea that, surrounding an electron, we know that surrounding an atomic nucleus there's an electron density there. It's just a question of going beyond the van der Waals radius of the atom and hypothesizing and speculating. There's a new region where electrons from the atom are tunneling all the time, or virtual electrons, I should say, are tunneling from the atom all the time, since it's not the same electron each time, and we know this because of non-local realism and whatnot. And they're tunneling at times to within the electroweak range of the proton in the other atom, and they're exchanging a W particle with the nucleus of the other atom, and that's pulling the atoms together slightly, creating a force of mutual attraction there between two atoms. And we can talk also about B.L. Hoo's stochastic gravity, and this idea that gravity is random. It is random, sort of. I mean, there's a demi-stochastic distribution, I'd have said, of electrons in a gravitational field. It's not as such stochastic, though. It's not quite totally random. It's still like a bounded continuum of stochastic processes or semi-stochastic processes of electron tunneling within the background. And it's a little bit more than that, since an electron is still more likely, very much more likely to appear within the primary probability density of an electron than it is in the secondary electron density at all. And if it does show up in the secondary electron density, it's still much more likely to be closer to the atom than it is far away from it, because it still has to adhere to the inverse square law of Newton. It still has to adhere to Newton's law of universal gravitation, and that still has to make sense, and this classical physics stuff still has to drop out of these quantum considerations. So I'm very, very much encouraged by what I was doing. I think this slight discrepancy, very, very slight discrepancy, really, between these two results could be explained by radiation pressure from the background. Really, it could be explained by the cosmological constant. It could be explained by tunneling electrons from all the other atoms in the universe, all the other particles in the universe, tunneling inside the box, releasing a photon here, there, and everywhere, and that just slightly skews the results, I think. Or that creates a very tiny little added bit of energy in there every now and then. So I thought I'd give you this update on my quantum gravity theory. I love you lots as usual, and bye bye bye. Have a great time out there doing whatever you're doing, and I'll continue to try and have a great time doing what I'm doing, which is physics research. Bye everyone, love you lots.